Hey everybody, Jerry here in the lab. Today we're going to be building this. This is a digital circuit that's going to drive a small 7-segment display, right? Something like that. And our circuit has a few components in it, a few 7400 series integrated circuit components like these that we're going to build on a breadboard. However, one of the integrated circuits I do not actually have. And it's actually the most important one. It's the chip that drives the signals to turn the LEDs for the 7-segment display on and off. So that little control sort of driver circuit, I do not have. So what we're going to do is we're going to take the digital gates and all the logic that's inside of that device. We're going to program that into an Altera MAX 7000 CPLD. That's today's video, and that's what we're going to do. So let's get started. Here we go. So we have a little circuit here, and we're going to be programming a small section of this overall little digital circuit. It's very simple, just, you know, and as a proof of concept of how these work, right? They operate at the same exact level, right, using the 5-volt digital logic TTL levels, and it can function exactly the same way as a 7400 series logic chip in a circuit that you build on a breadboard. Now, there's a few things that we need to do before we can build the circuit. To start, we are going to take a 44-pin PLCC socket like this one, and we're going to go over to my soldering bench, and I'm going to solder on a whole bunch of little tie line wires to build the circuit on a breadboard. So let's go and do that. Alright, so here's my workbench today, and as you can see, it is a complete disaster. Even Carl here knows how it is. This is Carl, the dangling robot. He knows how it goes. Right, Carl? When you're building stuff, you're going to make a mess. It's just how it goes. And that's how you know that you're actually doing something. Okay, so now that we have the soldering done for the PLCC socket, the next thing we need to do is to build a 555 timer circuit that we're going to use as the pulsating clock signal, right? Because any digital circuit, that if you're getting it to do something, they all need a clock source signal. That's sort of like the heartbeat of your circuit. and it uses that as a reference for, you know, everything that's happening in the digital circuit, all the switches turning on and off. It's always going to refer to the clock signal as the main source. So we're going to use a 555 timer chip, and we're going to build a small little clock oscillation circuit. So let's move ahead and construct that 555 timer circuit. Okay, so here we have a 555 timer chip that we have set up and configured here as an astable oscillator circuit. So we're going to be using that as a clock signal. So it's just going to be pulsating and creating a logic high and logic low clock signal for us. So if we turn on and apply power here and turn on this astable oscillator circuit, we should see the LED flash. So there I've applied power, charges the capacitor, and there it starts to oscillate. So there we go, it works perfectly. So we're going to take that 5 volt signal, the logic high coming off that LED, and we're going to use that to drive our counting sequence and having this 7-segment LCD display count up from 0 to 7 or 0 to 9, however we set it up. Alright, so the next step is for us to program our CPLD. And we're going to do that using a USB-Blaster. That's a JTAG programming interface. It's a little USB pod. And it has a little IDC connector that we can take 4 to 10 pins depending on the chip. And there's specific pins on this chip. It's called the JTAG programming interface. And we connect those pins directly to the USB programming pod. And then there's a feature of JTAG that's called ISP, and that stands for in-system programming. And if your chip supports ISP, it allows you to program a logic design onto the chip. Now most chips do support the ISP feature, and so in today's video, that's what we're going to be doing with this chip. We're going to be programming our logic design onto the chip over JTAG using ISP. And the software that we're going to be using to do that is Altera's proprietary software that they released back in the day, and that was called Altera Quartus 2. And so that was what they used to program all their digital designs onto various CPLDs and FPGAs. So we're going to go over to that software and we'll program our logic design onto this chip. Now before we can do that, we have to hook up our CPLD to the USB-Blaster. So we're going to do that on the breadboard, and I'm going to insert the Altera MAX 7000 chip into the PLCC socket, and then we're going to interface the USB-Blaster on the breadboard to the specific pins that are needed to program this chip. So we'll hop over and we'll do that now. Okay, so I've got this IDC socket connector here. And we're going to be using this to connect our USB-Blaster JTAG programming pod to our breadboard. And as you can see, I've got a bunch of the different connections here. We have power connected to VCC 5 volts as well as ground, and that's coming from my external power supply. So I've got a 5 volt power source connected here and wired up to this rail. And when I connect this line here, we'll have power on this rail. But right now I've just got it disconnected just while we're setting things up. As well, off this IDC connector, we have all the different JTAG lines, right? There's 4 of them. And so now, if we were to look at the Altera MAX 7000S datasheet for the component that we're going to be programming, you can see that there are dedicated pins on the chip, which are here, they're highlighted in yellow. These are the 4 JTAG lines, okay? This is the JTAG interface. And these pins, when your chip supports ISP or in-system programmability, you can use those pins to program the device when it's connected to a USB-Blaster, and that's the programming pod, okay? And they are TDI, TDO, TMS, and TCK. And those 4 pins are the JTAG interface for this device. Now you also have to make sure that you have all of your VCC and ground lines connected to your 5-volt power source when you're programming this. So it's important to note that you have to make sure that you have all your VCC and ground lines connected to your CPLD, but you also have to make sure that you have VCC and ground connected to the USB-Blaster and those specific pins on the JTAG interface for the programming pod. So there's dedicated pins there as well that require power and ground connections. I noticed that some students would usually think that the USB-Blaster was actually a power source and that it was providing VCC from the USB connection on the computer, but that's not the case. The VCC on there is just a VCC target, so it's detecting the VCC that's being used to power your CPLD device. So you have to make sure that you're sending that power source to that VCC target pin on the JTAG interface on the USB-Blaster. So just an FYI. So here's the PLCC socket, and I've got my Altera CPLD connected in there, as you can see. And we've got a whole mess of wires on the back here. Now this, of course, it just goes with the territory when you're prototyping, right? You're gonna have tons of wires everywhere. Now, ideally, you could build yourself a little PCB that would accommodate this PLCC socket, and it would provide you with a couple of headers that you could just plug in right down on your breadboard. But if you don't have that, and all you have is the socket, then you're gonna have to resort to using tie lines and just connecting a bunch of wires here that you can plug in directly into the breadboard. And that's what I've done here. So we got a whole bunch of wires here. Now don't get too frazzled by it, don't get intimidated. It's a big mess. We got a big rat's nest here, but that's okay. So now I've got all of these red wires and these white wires. These are going to be serving as our IOs for when we're building our circuit on the breadboard to drive the 7-segment display. So these are all of our IOs, so we can just ignore those for now. Now, and when you look at the data sheet for our CPLD, there are dedicated VCC and ground. That's the power supply pins to power the chip, right? So you have all the different ground connections as well as VCC, which is going to be connected to our 5-volt power source, okay? And so here on the PLCC socket, you can see that I've got all of these blue wires. Those are the ground pins, and I've got them all combined into one wire here that I'm going to connect to the ground on the breadboard. And then as well, I've got all of the VCC connections all connected to one wire, and we're going to connect that when we need to power the chip. And I've also got 4 separate wires here that you can see, and these are color coded. I've got green, brown, yellow, and white, and these are the JTAG programming pins for the CPLD. And again, when you look at the data sheet, you can see them laid out, and I've got them highlighted here in yellow. So you got TDI, TDO, TMS, and TCK. And I've got them color coded, so these just match up. So we'll go ahead and connect those. So we've got our brown, and we've got our green, and we've got our white, as well as the yellow. So that's the JTAG programming pins. So that's should be ready to go for when we hook up our USB-Blaster. Now you have to make sure that you connect VCC and ground as well to power the chip. So we're going to make sure we do that. So I'm going to take the ground here and we're going to patch in here to my ground as well as VCC, and I can go ahead and connect this because we actually have it disconnected here at the top, so there's no power there yet. So we'll go ahead and connect that. but I won't actually power it until we're ready to go. Okay, so all we have to do now is connect our USB-Blaster and the IDC connector. We'll just plug it in here, and then when we're ready and we have the software booted up, we can then go ahead and apply our 5 volts for VCC, and that's going to power the CPLD. So you just have to make sure that you're using an external power source for VCC and a 5 volt signal there to power your CPLD, and then the USB-Blaster will also reference that voltage. All right, so we're going to activate Quartus 2, and I'm running version 9. There we go. And so we're going to design our logic for the 7-segment display driver circuit. Now, what's awesome about Quartus, if you don't already know this, Quartus actually provides the entire library for almost all 7400 series logic devices and the logic that they contain, and you can implement those when you're using the graphical user design interface. So we're going to use that, and we're going to load up the 7447 logic device or integrated circuit, which is a 7-segment display driver chip. Okay, so we're going to start a new project here. So we're going to go down to New Project Wizard. So we're going to create a folder called 7447 7-seg driver. 7447 is the number of the integrated circuit chip. And we're just going to call it 7-seg driver. Okay. And we'll go ahead and click Finish. Okay. So now we're going to go up here to say File New, and we're going to take a block diagram schematic file. That's going to be our design entry. Okay. So we'll hit OK. So this is our schematic entry design file, and what we're going to do is we're going to go over here to Symbol Tool. So we're going to activate that, and then in our Quartus install directory, we're going to hit the plus symbol, and then we're going to go over to Others, and then we're going to go under Max plus 2. Okay, this was the original software that was developed by Altera, and as you can see here, we have all sorts of different types of logic components, right? So here's the 7400 series. This is the beginning of it. So we have a NAND gate there. So if we navigate down, the component that we want to use to program into our CPLD is the 7447. And what that is a BCD to 7-segment display driver chip. Okay, so we're gonna have to navigate all the way down so you can see there's all the different types of 7400 series chips and all of the logic that those devices implement. These design files essentially will implement that design for you. So here we go. I jumped ahead of it here. There it is, 7447. And as you can see, we've got that BCD to 7-segment display device implemented and designed here by Altera for us, and is available as a logic device. So we just select OK, and here it is, and we can place it anywhere within our design file here. So I'm just going to place it right in the middle, and there we go. Then we hit Escape to get rid of that. So now if we double click on this, okay, you can see that here we have the same exact logic design of a 7447 BCD to 7-segment driver. If you were to load up the data sheet for that particular 7400 series integrated circuit, you would see that this is what it contains. This is what it is able to implement. And as you can see here, it's designed by the Altera Corporation, okay? And it contains all the different logic gates and all those interconnections. And then it has all the outputs here that are designated, as well as all the different inputs, right, that are connecting. And this whole chip is designed to properly trigger and activate the different LEDs that are on a 7-segment display. When we use this, we have this bus here. We have A, B, C, and D. And when we apply a counting sequence in binary format on this bus, okay, on these 4 pins, and we run through a counting sequence in binary, it's going to properly activate the output signals here to drive the proper LEDs on a 7-segment display so that it displays the characters accordingly to whatever value on a clock counting sequence that we have, okay? So that's what's really cool about this device. So now, we'll go back to our design file here. And so what we're gonna do now is we're gonna insert some inputs and output pins, okay? So what we're gonna do is go back to our symbol tool here. And now this time we're gonna navigate up to the top. We're gonna minimize these. And we're gonna select primitives, okay? And then under pin, we have input, output, bidirectional if we're doing some kind of a data bus. But in this case, we're looking at the input pins and the output pins. So for now, we're going to select input pin. And all of our inputs here are here on the left side of the device. So we're going to place an input pin for each of these pins on this device. And there we go. So I'll hit escape. And now we're going to connect these to these inputs on the device. We're going to use the node tool. We'll activate that, and then we simply make connections between each. Here we go. And now we're going to create the output pins. So now we'll select output, and we're going to place output pins. Okay, and now we'll do the same. We'll select our node tool. Here we go. Okay, so once we have all of our inputs and output pins applied and connected, we're then going to save the project file. So we'll say save, and we're going to call this 7-segment driver, and we'll hit save. Okay. Before we do anything, now that we've added all of our inputs and outputs, we're going to go up here to assignments, and we're going to assign a device for our schematic. Okay, so now under the family name, we select a drop-down menu here, and we have all these different logic families that we can choose from. So the chip that we're programming today is the Altera MAX 7000S series, and that's the JTAG compliant device. Okay, it allows and supports the JTAG programming interface. So we're going to select that, and then we're going to navigate down to the EPM 7064 SLC 4410. Okay, and then we hit OK. So now, in order to properly map the inputs and outputs to the physical pins on the chip, on the CPLD, we have to do that using a menu option in the software called Pin Planner. But before we do that, we're going to properly name our inputs and outputs. So for this pin here, we're going to call it A, right? Because it's the designation of what the function that it serves on the actual chip. So we're just going to maintain those. So then we have B and BIN. Okay. And then we have output A. Output B. There we go. So now these have all been properly assigned based on the inputs and outputs and their designations. So now we will save this. And now we're going to go to our Pin Planner. So we're going to go to Assignment and Pin Planner. And Oh, right. And so as you can see here, they still have the old names. That's because we didn't run through a compilation. Now that we've changed this, we're going to run through another compilation. So we'll run through the compilation process again. Okay. Then we'll go OK. And we'll close this window. Back to our design file. And now if we go to Pin Planner, you'll see that it has the proper designations for those inputs and outputs. Okay. Okay, so for our node A, which is our input pin, we're going to assign that to pin number 4, and that's an available I/O. Okay, and then for node B, we're going to select pin 5, another I/O. Okay, and then RB on is pin 17. And then we have TCK, TDI, TDO, and TMS. Those are the JTAG programming pins. So we don't have to assign those because those are already assigned by default. Okay, so we can just go ahead and close this. And now we're going to hit save the project, and then we're going to run through a compilation sequence again. Okay. All right, so now we should be ready at this point to program our CPLD. So we can then go up to Tools, and we're going to activate the Programmer. Okay, so this is the JTAG programming window, the programming tool. And what we have to do, we have to make sure we have JTAG selected, which we do. And you can see here that our compiled POF file, that's a program object file, and that was created when we did the compilation. And this contains all the logic for our circuit. And this is what we're going to be programming onto the CPLD. So now, under hardware setup, we have to go in and select the USB-Blaster. So as long as you have that USB pod plugged in, which we do, click here, and there it is there. That's the available hardware. So now we have to say the currently selected hardware. So as long as you have your USB-Blaster connected, this means that your drivers are installed and everything's working. If it's not, you have to go in here and add hardware and configure your drivers. So then here for Quartus, under currently selected hardware, we select USB-Blaster, and then we hit close. And now you can see here that it's available and selected. So now all we have to do is hit start. We have to make sure that this is selected. As well, we have to make sure that we have program and configure. That's the one you want to make sure you have selected. Okay, so now we just hit start and it should program. We got an error here, hang on. Okay, so it's not detecting it. So it's possible that our power, there might be a VCC or a ground disconnected here. So let me check very quickly the VCC and grounds on the PLCC socket. I'm pretty sure they're good, but we'll double check. So I'll just hop over there very quickly and validate that we have VCC connected and powered properly to that PLCC socket. Okay, so I just wanted to show you guys this. This is my logic probe, and this tool essentially is for testing digital electronics and digital circuits. And so, of course, with digital circuitry, you're always dealing with 0 volts and 5 volts, right? So you have VCC, which is 5 volts, and ground, which is 0 volts. And so on a board here, we have our power rails, which have 5 volts for the red side, and then you have 0 volts for the blue side. And so that's VCC and ground. And on the logic probe, whenever you connect the tip into those different areas on the board, if you connect it to an area that's reading 5 volts, it will show up as a logic 1 or a logic high. And when you connect it to ground, it will show up as a logic low. And so I'll just demonstrate it here. So if we connect it to the power rail here, and the red side is 5 volts, you can see how it's showing up as a logic high. And when we connect it to the negative or the ground for 0 volts, it shows up as a logic low. So you use that for testing different areas of your circuit. So on the 555 timer here, if we connect to the pulsating output for the clock circuit for our clock signal, you can see how it's alternating between 0 volts and 5 volts, logic low to a logic high. Okay, so I've validated all of our VCC and grounds on the PLCC as well as on our JTAG USB-Blaster. So this should be working. I'm going to try one more time here. And we're still getting the error. This should have programmed. You know what? We've fallen into a condition here where the JTAG cannot be programmed yet. This is actually something good to talk about, but oh man, Carl is not going to be happy about this. Carl, we're in JTAG lockout. Calm down, Carl. Carl, relax. Carl, it's not a big deal. Okay, so let's talk about JTAG lockout. What is it? And when does it happen? So we're talking about Altera MAX 7000S devices. That's JTAG compliant devices. And that's the one we're using today. JTAG lockout is a condition only when you buy your CPLD devices used. Okay, so if you buy them off eBay, or if you did what I did, which is a dumpster dive, and you got your device as, you know, a system pull, right? Popped it out, thought great. Got an Altera MAX 7000 JTAG compliant device that I can plug in and program and do all sorts of cool stuff. However, so if we look at the Altera MAX 7000S datasheet, and you look at the pinout chart, right? The pinout diagram for the device. And on the JTAG programming pins, which I have highlighted here in yellow, you'll notice that each pin has a bracket and it also shows I/O. Okay, so what that means is that there's a secondary feature for those pins, and they can be used as additional I/O pins, you know, as part of a digital design. That's what's happened here. So now the only way to re-enable the JTAG interface and get those pins to go back to their factory default state is to erase the device using a non-JTAG programming system. Okay, and you do that by using universal programming systems. So there's companies like Data.io. This is the Data.io Unisite. That's a system that I have, and I've shown it here many times on my channel. It's able to program EEPROM memory, microcontrollers, CPLDs, and FPGAs. It can program different package types as well. There's different adapters that you can get, and you can get DIP packages, PLCC, you can get SOIC, quad flat packs, BGAs, you know, all sorts of different types of adapters are available. Now, Altera also came out with their own version, and this is actually the system that they use to program all of their CPLD and FPGA devices before JTAG was even available. And that system was called the Altera Master Programming Unit. Okay, and it used a special ISA card. That was the LP6. They had different versions before that, but the main one was called the LP6 ISA programming logic card. And you would interface that to a special adapter base that would accommodate different adapters. And these were called Altera MPU adapters. And this was the system that Altera used to program all of their devices. Okay, so technically if you had one of these Altera Master Programming Units, you could also use that to erase your CPLD device. Today we're going to use my Data I/O Unisite Universal Programmer. So we're going to hop over to my bench and we're going to take our CPLD that is currently in the JTAG lockout state. We're going to pop it into our PLCC socket adapter, and we're going to perform an erase function. So we'll hop over to the bench and we're going to erase our CPLD, and that's going to re-enable and reactivate our JTAG interface. So this is one of my universal programming systems. This is the Data I/O Unisite. This is just a massive machine, but it's incredible. It can program thousands of different devices, not only EEPROM memory chips, it can program flash, microcontrollers, the older GALs and PALs, those types of logic devices, CPLDs and FPGAs of all different types. It has different socket adapters that you can hook up to the top here with different modules. So this is one module called the PPI base, and you can hook up different BGA sockets, SOIC sockets, quad flat packs, all different kinds. And it's just an amazing system. And this is one of the units I have. This is the Data I/O Unisite. I also have a LabSite, a flash pack, and they're just incredible. They can program just thousands of different devices, and anyone that works in retro computers, arcade machines, pinball machines, they'll know about the Data I/O Universal Programmers. They're just incredible. Okay, so to erase the device, we're going to navigate down to our more commands. Okay, and then we do, we do device checks. Okay, and then we can do blank check, electronic erase. Well, first we'll do a blank check, and now this should be programmed. So this should come back as a programmed device. So we have to insert the device. So we'll open up the matchbook here, and we'll insert our chip. Close the matchbook, lock it in. Okay. And now we'll run the blank check and execute. Non-blank device, so operation failed. That's correct. So in order for us to erase this, we'll go down. So we say previous menu. Okay, and then we'll say device checks, and then we'll go down to electronic erase. Okay, electronically erase device, execute. Operation complete. Okay, so now this should now have the JTAG interface re-enabled. Those JTAG pins on this device should now be operational once we hook it up back on the breadboard and we use the USB-Blaster with the JTAG programming interface. So we'll close this down, and we'll switch over back to our workbench, and we'll check to see if we can program this with the Altera Quartus software. Okay, so we'll just reinsert our chip back into the PLCC socket, and you make sure that you have the corner here aligned properly with the socket. So you just want to make sure you get that in in the correct orientation. We'll just place it in like that. And then we just snap it into place. And so we'll just plug in the USB blaster, power up the circuit, and we should be good to go. Okay, so I've got power applied. Hook up our USB for the USB blaster. Power's applied, so we should be good to go. Okay, so here we are back using JTAG, and we're going to try this again, third luck's a charm. And so now technically the JTAG interface on the CPLD should be enabled because we performed the erase. So here we go, we've got it all connected, it's all powered. And now if we hit start, yay, it's running. Fantastic, you see? There we go, everybody. Yeah, successfully performed operations. Fantastic. Now this was a perfect example for this video today, and to demonstrate how JTAG lockout does happen. Okay, so we can close this, and we're now going to go over to the breadboard on the workbench, and we're going to build our circuit, and we can set everything up with the PLCC socket operating as the 7447 BCD to 7 segment display. Okay, so the parts that we have for this is our 7 segment display. We also have the 74LS193, that's our synchronous 4-bit up-down binary counter. We also have a 74LS00, that is a quad NAND gate, and that's essentially what's going to be allowing the clock signal that's coming from our 555 timer to be routed into the 74LS193 counter IC. And we also have a 74LS42, and that's a BCD to decimal 1 of 10 decoder chip. And essentially what that's going to do is it's going to determine which number is our maximum number for the counter and the counting sequence. And so depending on the output pin that you use, that determines which is the maximum number. So if you select output pin 5 or 6 or 7, that will be the maximum number reached in the counting sequence and displayed on your 7-segment display. So these connector blocks I'm using, these are called Wago wire-to-board PCB terminal blocks. And essentially what these are is it's a quick way to allow you to interface some wires. So I'm going to be using these because it's going to allow me to interface the 30 gauge wire that I have soldered to the PLCC socket. And those wires are pretty small, and so they don't connect well on the breadboard. So by using these little connector blocks, I can easily put in the 30 gauge wire into this contact, and it'll provide me with a connection block that can easily be connected to the breadboard. And then I can just interface some regular gauge wire for interfacing the other components. outputs. 18 is add. Okay. Is the bottom. Oh, Jesus Christ. You gotta be kidding me. Did I just fry this thing? You've got to be kidding me. You have got to be kidding me. Oh my God. I think I may have just fried this. Oh my God. Wow. So yeah. Oh my God, I cannot believe that that happened. Of all the years that I've had my power bar down here along the bottom edge of my bench, I have never had an issue where I was accidentally short-circuiting some parts. All the years that I've had this, 15 years, I've never had that. That's unbelievable. I could not believe when this happened. I mean, the odds of this happening, and be ready for the unexpected, especially something like that. And what sucks is that that was the only part I had that was a 44-pin PLCC. So anyway, thank God I had a whole whack load of the 84-pin PLCC devices, and those were the Altera MAX 7128S LC84. So I rigged up a socket for that very quickly and went through the motions of, you know, going through the erase process with my data I/O unit and hooked it up to the USB-Blaster again and reprogrammed the design from the Quartus software over JTAG ISP and got it reprogrammed. So we're back, ready to go. The chances of that happening, what are the chances? Okay, so the circuit's complete. We've got our 555 timer up here at the top, It then sends its pulses down here to the quad NAND gate, which then dictates when the clock counting pulse will be fed to the 193, that's the 74 LS193 synchronous counter chip, and the counting sequence is sent out in binary over these blue wires here. This is the output data bus for the counting sequence, and those binary signals are then read here by the Altera MAX CPLD on this bus here, which comes in here on these white wires. The bus is also monitored by this 74LS42, and that essentially is a decoder chip that's sending out a logic low pulse over to the quad NAND gate, and that essentially dictates when to halt the counting sequence, and it stops the logic pulses coming from the 555 timer, and that halts the counting sequence. And so by selecting a specific output on this chip, we can then dictate which number the counting sequence will stop and where it halts. So I've connected this to the output of a digit 9, and so it should halt the counting sequence when it reaches the number 9. We also have our output signals for the 7-segment display, which are fed over these red wires, and so these are the logic signals to engage the 7-segment display. Now, one thing to mention is that when I was testing the CPLD, I noticed that I had programmed the wrong 7400 series logic device onto the CPLD. It was actually the 7448 that we needed because it generates a logic high pulse output for this particular type of 7-segment display. It requires logic high pulses to activate the LEDs, and the 7447 is a logic low a 7400 series device. So I just reprogrammed that very quickly with the 7448, and that provides the logic high output pulses on the data bus there for the 7-segment display. So I'm just going to turn on the power and it should start counting. So there we go, power has been applied, and so now to actually engage the counting sequence, I have to press this little push button here, which is sending a low pulse to the quad NAND gate in order to start the counting sequence. So I'll just activate that and it should start counting. 0, 1, yep, there it goes. Awesome. Fantastic. 3, and it should go all the way up to 9. 6, 7, 8, 9. There we go. Awesome. That's awesome. That's so great. So that just shows you how, using these Altera MAX CPLD devices is just so awesome, because you can implement any type of digital logic design, different gates and whatnot, or different devices that you can design or that you can use that's a part of the software, and implement a fully digital logic design setup using CPLDs. It's just a fantastic device. All right, everybody, that's today's video, getting to mess around with Altera MAX 7000 CPLDs from the 90s. What's more fun than that? Especially when you fry them with 115 volts. Unexpected, be ready for the unexpected. The more you tinker with stuff in the lab, you run into stuff that you don't expect. Every day is an adventure, but man, so much fun. And I really hope that you guys enjoyed this project here that we tackled. And maybe you guys can jump in and do some of your own implementations on Altera MAX CPLDs. Loads of fun. So thanks again for watching, everybody. Please hit the like and subscribe if you can. It's always appreciated. And we will see you in the next video. Take it easy and bye for now. Ciao.